Okay, so on this one, what's it asking you? It's actually, this is a, what type of integral is this? What type of it? Definite integral. Why is it a definite integral? It has a set area, yeah. So this will evaluate to a number, exactly. Okay, so if you're going to do this, you need to find the antiderivative, or you just need to know what the antiderivative of secant squared. What's another way of saying what is the derivative of secant squared? What is another way of saying what is the integral of secant squared? What function has a derivative that is secant squared? Like, think of it as Jeopardy. It's go the opposite direction. What function has a derivative that is secant squared? Anybody remember? Yeah, it's just this is just going to be tangent x from what to what? 0 to pi over 4. So this is going to be tangent of pi over 4 minus tangent of, what is tangent of pi over 4? Oh, come on. Over root 2 over 2. 1 minus is done. That's it. So the way you think of this is, you think of this as what function's derivative equals secant squared t. Like that. What function's derivative equals secant squared t. That's what you need to think of it as. It's actually something we could talk about. Okay, so you did this. You did the integral from 0 to pi over 4, and instead of secant, what did you write? 1 over cosine squared t? Okay, hold on. So then you rewrote it as pi over 4 cosine to the what? Cosine squared t to the what power? So you wrote it like this, and then you tried to find the antiderivative of that. Really hard. Really hard. What I mean by really hard is you can't just undo the power rule here, because what's 1 up from -1?
Oh,
Zero, right?
That'd be like the natural law.
You run into that sinkhole of you can't just raise something into the 0, because what's anything to the 0 power? 1. And is that what we want? No. The other problem you have, if you do this, you have to be really careful about the cosine squared right there, because if you take the derivative of something squared, what happens? Yeah, the chain rule is going to come into effect. I will say it this way. This right here, this is not technically incorrect. Just be careful. And there's 2 reasons you don't want to do this. 1, it's really, really hard, even if you were to find a way. And 2, this way right here, super easy. Second thing, go ahead, yeah?
What
you're saying? So you're saying you want to do this. You want to do this to pi over 4 of cosine to the -2. So another way to write that, in other words, you want to write it like this. Cosine t to the what power? Yes, that is absolutely correct. Sure, absolutely.
The antiderivative is...
What do you think it's going to be?
-1/2 sine -2.
Times what?
To the -2.
So sine t to the what? You think that's the antiderivative, right? If that's the how do you check to see if that's the antiderivative? Hold on. How do you check to see if something is the antiderivative of something else? Take the what? So take the derivative of this. What happens? What happens? You kick out a cosine. I will tell you this. Because what's the derivative of sine? That would be sine cosine right there. But here's the thing. You have to be really careful. I will tell you this, just to give you a side story right here. This right here is hard to do. This right here is not easy. This is something you will run into. It's not that bad. The problem is anti-differentiating cosine squared, you run into the chain rule when you start testing things just out of your head. And I will say you have to use, I will tell you what it comes back to. You end up having to use an identity which is directly related to the sum of the double angle formula to do this one. I could explain to you how to do this one, but it's not something you need to know how to do right now. So, Carter, just to answer your question simply, when they give you something like this, you need to recognize that secant squared is the derivative of tangent, okay? I like this. Just be really careful. It's really easy for me to give you something that looks a lot like something you can work with, but is totally not. My favorite example, or one of my favorite examples, are solving things like this. How about this? E to the x minus 4 is equal to x. E to the x minus 4, it's an exponential function, right? You can kind of see, where does that cross the y-axis? It crosses at negative, well, it crosses -3, right? When x is 0, it's so it's -3. Y equals x goes up at a slope of 1. So does the function y equals x, does it intersect this function? No, it does. It just, it does. Look, y equals, this right here represent e to the x minus 4, right?
Yeah.
Sorry, it goes down, right? Because what's e to the negative a little bit? Yeah, so it goes like this. Sorry, excuse me. Doing this wrong. When x is 0, it's -3. So it goes like this, right? What does y equals x look like? It looks like that. So do they intersect? Yeah, they absolutely intersect. Finding the intersection by hand algebraically is ridiculously hard. Ridiculously hard. So just because it looks like something you can deal with doesn't necessarily mean it is something you can. They're asking you to find the derivative. They're asking you to find h prime here, right?
Yeah.
So what do you plug in for x? So you know h prime of x is going to be arctan of what? 1 over x times what? Negative x to the -2. You have to multiply by negative x to the -2. Why do you have to do that? Yeah, well, you have to do that. You're applying the chain rule. The derivative of this is there. The derivative of x to the -1 is negative x to the -2. That, okay? If I asked you to find n prime, what's the problem? What do you notice? What's the problem on this one? There's no what? There's no constant, right? Where do you want the constant to eventually be? The bottom, the lower bound. So there's no constant. Does it really matter for you if the constant's on top? Because what can you do? You can just flip it, but there's no constant here. Yesterday I gave you an identity. I gave you something yesterday. It was one of the last things I gave you, and I thought the homework was going to ask it, but I guess I just need to actually write the question in. I gave you this. The integral from a to b of f of x dx, or let's say, I'll be more clear. Let's say it goes from a to c, is the integral from a to b of f of x dx plus what? B to c of f of x dx. Now here's the thing. You're going from a to b and then you're going from b to c and you're adding them together. It's basically saying 6 is equal to 2 plus 4. You can pick any number you want. Does it necessarily have to be between the variables? I'll just tell you right now, it doesn't. It can just be any number you want it to be. But if you're arbitrarily choosing and it doesn't matter, what number is a good number to choose? 0 or 1, right? In this case, you're not even plugging the value. Are you even plugging these values in? Like if this was 7, does it affect the derivative? No, it doesn't affect the derivative at all, right? So it doesn't really matter, but by and large, if you have a choice of a number to pick, what number should you pick? 0. So what is n of x going to equal? What is n of x going to equal? Well, hold on. We're going to break it up. So it's going to be x squared to what? 0 of cosine t dt. And what are you adding to it? 0 to the square root of x of? Ah, yeah, good job. Now there's still a problem. What's the problem here?
The constant on top.
Constant on top. Where's the constant on top? Right there, exactly. So n of x is equal to, what do we have to do to the first one? Negative 0 to of cosine t dt plus 0 to the square root of x of cosine t dt. Now can we apply FTC part 1? Yeah, now it's FTC part 1. Yay, FTC part 1. Wonderful. Now it's just plugging stuff in. So what is n prime going to be? Negative cosine of times what? Times 2x plus cosine of times what? 1/2 x to the... If I gave you this question and you left it right like that, that's fine with me. On the AP test, they might, in a multiple choice, what are they going to do to that? They're going to clean it up a little bit, you know? So what my guess is they would write it as, if I was guessing how they would write this, they would write it as the following. Cosine the square root of x over 2 root x minus 2x cosine x squared. That's how I think they would write it. They would get rid of as many negatives as, not get rid of, but rearrange it so the negatives weren't sticking out in front. This is how I would say if it was a multiple choice. Could this be a multiple choice question on the AP exam? Absolutely. Because it's really easy for them to make up things that are wrong that look right. It's really easy. And is this a good question? What I mean by that is, let's say I had a function. It's one function. So let's say I had a function that looks like this. Like this. So this right here is your f of x. And let's say you were going from here, let's say we're going from A all the way to C. Now, if B is between, let's say B is right here, B between, does this plus this equal the whole thing? Yeah. Pretty clearly it does, right? But let's say B is outside. So let's say B is over here. Let's say this is b. So let's go from a to b. What do you end up with? You end up with this thing, right? Is that value going to be positive or negative? Negative, because you're going backwards, right? And then what do you add to that? Then you're going to add all of this, which is going to be positive, but what's going to cancel out? Yes, this will cancel. And what are you left with? A to C. So does it matter where B is? Not at all. Then again, it doesn't really matter what B is at all, so what are you going to choose? 0. Asking, find the interval in which the curve y is concave up. When is y concave up? When what is true? When what? You said it. So we want to know when y double prime is what? Positive, right? So can someone just tell me, what is y prime? 1 over x plus, which is the same thing as 1 plus x plus to the what? So what theorem did we just apply? FTC number 1. 2 is if we get a definite answer. 2 is if we take the integral of the top of integral of the function evaluated at b minus the integral of f evaluated at a. This is FTC part 1. So now what do we do to this? Take the what? Take the derivative. What's the derivative going to be? Fun. Negative. Just look up here. You don't need to look at your work. Fun. Just look at the board. Negative. No, just do the whole thing. Hold on. Just do this. 1 plus x squared to the what power? Times what? 1 plus 2x. Yeah, I just wanted to do that. Now, does it simplify a little bit? Yes. It's going to be negative 1 plus 2x all over what? To the power of 2. Yeah, fine. What you were doing is you were kind of just going to the end. You wanted to put the 1 plus 2x first. Just do it this way, just so we have one more step. That's all I wanted you to do. Okay, so now we're interested in finding out where this is what? Because, yes, you both said true things. We want to know when it's greater than 0. So in our quest to find out when it's greater than 0, we're interested in finding out when this is equal to 0. Well, you know that this right here is always what? That's one observation, but how do you make a fraction equal to 0? So negative 1 plus 2x has to be 0. So therefore, 1 plus 2x has to be 0. So 2x equals negative 1. So x is negative a half. So now we have this right here, negative a half. This is the x value, and we want the y double prime value. So we know, what's the y double prime value when x is negative a half? 0. We know that. That's the whole point of what we just did. So now we need to know what happens to the left and to the right. Well, the bottom is always, as we pointed out, what? Positive. What's to the right of negative 1/2? That's really easy to plug in. 0. Plug in 0. What do you get? Negative 1 over, actually over 1. So you actually get negative 1. So this is definitely negative. What happens when you plug in negative 1 into this? What's 1 plus negative 2? What's 1 plus negative 2? What's negative negative 1? So what's it going to be? Positive. So where is this concave up? So it's concave up from to what? To negative 1/2. Do we make hard brackets on either of those ends? Why not? Why don't I put a hard bracket right here? You can't reach infinity. And why don't you put a hard bracket here? Because it's not concave up there. The second derivative is 0. Doesn't have concavity right there, which is something we should look up. But it's not concave up, because to be concave up, our definition is the second derivative must be positive. Is 0 positive? No. Do you understand what they're asking? They're saying evaluate the limit by first recognizing this as a sum, recognizing the sum as a Riemann sum for a function from 0 to 1. So what it's telling you is this is equal to the integral from what to what? 0 to 1 of some function. If you had the function, can you use FTC part 2? Yeah. But we need to recognize what the function is. So you need to pull this apart a little bit. So the thing you should remember is you wrote this a few times. Limit as n goes to infinity, I equals 1 to n. What's the width of the piece always? It's the width divided by n, right? 1 over what? 1 over n. What's left if we pulled out 1 over n? What's left inside? I cubed over what? N cubed. I cubed over n cubed. What's another way to write I cubed over n cubed?
1 over n cubed times I cubed.
well, no, 1 over n. They're both raised to the third power, so what can you do? Oh, I'm sorry, you said it. I just heard it wrong. I over n to the what power? Cubed. So, can you recognize what the function's going to be? This is equal to the integral from 0 to 1 of what? It's not 1 over x cubed. What's happening? Remember what you plug in on the inside is not the function, right? This is not the function. Where does this thing start? You know that it starts at 0, correct? And how far over do you go after the first one? You go over 1 over n, right? And then how far over are you? 2 over n. And then how far over are you? 3 over n. And you know this is going all the way to what? N over n, which is what? 1. We know it's n over n, which is 1, right? What are you doing to each of those values? No. What are you doing to each of those values? You're cubing it. So what's the function? Yeah. That's all this is. This right here is how you would write the Riemann sum of this integral right here. We did this last section. They made it a little harder by what did they do? They just combined it, right? They just simplified. Usually we started here and we went backwards to this, and then what could you factor out? I goes from 1 to n, you could factor out the 1 over n to the 4th. In order to do this integral, you need to know what 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, all the way to n cubed. Is that very nice? No, it's not very nice. But this right here, you recognized as x cubed, so what is that going to be? What's the integral of that? 1 over?
1 over 3.
Nope.
1 over 4.
4 x to the, from 0 to? And what's that equal? It's pretty easy.
0, 1/4.
Yeah, 1/4. Done. Why is it 1/4? Plug in 0 into that. What do you get? 0. Plug in 1. What's 1 to the 4th?
What's you get 1/4?
You get 1/4. Yes, you get 1/4. They already told you. They go from what? 0 to what? 0 to 1 of some function. Again, what's the width of this function going to be? Yeah, and we need to maybe, if you want to rewrite it like this, let's try to rewrite it like this. You know it's going to be 1 over n. This right here, see this right here? What are the pieces equal to? What's the first piece? 1 over n. What's the second piece? 2 over n. So what are you doing? The square root of? This is another way to write that. This you're right. I'm just rewriting it with summation notation. You're starting with 1 over n and then what? 2 over n and then 3 over n. I mean, if I wanted to write this out totally in the proper order, I would write it like this. The limit of 1 over n like this, not pull it out, and then do it's the summation of I equals 1 to n. Like that. Is there any I in this 1 over n? No. So can you put it here if you wanted to?
Yeah.
Or you like putting it out there, right? So let's just write it in the way you've mechanically written it a few times so far. This right here to n of 1 over n times I over n to the what power? To the 1/2. And what is that equal to? That's the integral from 0 to 1 of what function? X to the 1/2 dx. That's all it is right there.
So
that's all it is. Integrating this, it has to go to the what power? 3/2. So what's going to have to go out front? 2/3. And you're going from 0 to 1. And what's that equal? 2/3. Is it nice when you're going from 0 to 1? Yeah. Okay, so I'm going to modify this just a little bit. Yeah, now it's going from 1 to 2. Because if this goes to n, what's n over n? What's 1 plus 1? So this equals, just to go straight to the integral notation, not 0, sorry. It goes from what to what? 1 to 2 of 1, sorry, of what? Sorry, excuse me. That's this x to the 1/2 dx. The only thing we changed was the starting value. So I'm going to change it a little bit again. I haven't changed anything. Have I changed what you're doing to the input values? I have to change this because it has to now go from 4 all the way up to 7, right?
Why to 7?
Why to 7? The big clue is this right here. You see that?
Oh, because the width.
Has to go. The width is what? 3. Another way, I wrote it a little bit vague because I wanted to see what would happen here. Another way I could have written it is like this. About this. So G is the integral, is the area under the curve from 0 to wherever the x value is. So if G is traveling along, let's say the x value is right here. I'm filling it up. Is it positive or negative? Positive. So if I go a little bit further, does G get bigger? Gets bigger, 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 right? So here, G of x is positive. the area is positive in there. And it's not really g of x is positive. You can just say that the area under the curve there is positive. It's kind of bad to say area isn't positive, but the net change is positive. And then what happens? Negative. So, right here, it's negative. So you're right, Carter. Do you know the exact y values for all of these? No, we don't know the exact y values because we don't really have a function. You can estimate the area under those curves, but do we have a function for f of t? No. But we know that the maximums occur when what? X is equal to 1. Where else? 5. And where else? 9. Because what happens immediately after 1? It starts, g of x starts to decrease. And what happens immediately after 5? G of x immediately starts decreasing. And what happens immediately after 9? It looks like it's going to decrease. Well, it's been increasing up to that point. So where do the minimums occur? X equals 3. Well, actually, you could say 3. Where else? 7. And there's another one you could put in there if you wanted to.
0.
Yeah, if we're putting 9 as a maximum value, 9 as a place where a maximum could be, you can put 0 as a minimum. So the second question there, where does g attain its absolute maximum value? Looking at that, where do you think it attains its absolute maximum value? What x value do you think it gets to its absolute height?
5.
You sure?
1.
Is it at 1? Well, this is where you have to look at the relative size of those bumps. The relative size. So let's call this bump 1, then 2. Actually, using that as a value is bad. How about A, then B, then C, then D, then E? It looks like if they were all positive, what sizing-wise, A looks like it's the smallest, then what? B, and then what's the next one? C, and then it looks like E might be a little bit bigger. I think E is at least as big as D. E is at least as big as D. So if that's the case, look what happens. You start off with this little bump A, right? And then you take this away, but then do you add in more or less than you just took away? More. You're adding in more than you just took away. Then you take some out, but then what do? You add in at least as much as you took away. So where do you think the absolute max is going to occur?
9.
X equals 9. Just separate from this question a little bit. We're going to write the same thing. What was g of x equal to? The integral from 0 to x of. The fundamental theorem of calculus part 1 tells us, what does g prime of x equal? F of x by FTC part 1. FTC part 1. So, what are we looking for again? We're looking for where the second derivative is. So what is the second derivative of this thing? F prime of x. So we're looking for where f prime of x, so we want to know when g prime of x is less than 0. That's the same thing as finding what? Where f prime of x is less than 0. So do we actually have a graph of f of x? Yeah, that's f of t. You can just change what t is called to x. It doesn't change anything about the shape here. So we're asking ourselves, where is the derivative of this function negative? Where is the derivative of this function negative? Looks like from here to there, from here to there, and from there to there. So purple is f prime of x is less than 0. So what are those intervals? What does it look like those intervals are? 1/2 to 2, union 4 to 6, union 8 to 9. Fundamental theorem of calculus part 1. That's it. And then could you sketch a graph? Yeah, to sketch a graph, you'd have to estimate those areas. What shape do these curves vaguely take on? What do they vaguely look like? They look like what? Make it simpler.
Circles.
No, they're triangles, thank you. Just go real simple. Like, go simple. They look like triangles. So you could estimate using triangles. When they say sketch a graph, is it going to be exact? No, it's not going to be. What is a definite integral? Has a set area. It has an answer, a numeric answer, right? An indefinite integral won't. It's a simple way of saying it. But let's say, is this an definite integral or an indefinite integral? This is a definite integral right here. What would I have to change in order to make this indefinite? Oh, look, it's an indefinite integral. All this is asking us for is, what is the indefinite integral? If I ask you for the general antiderivative, that's what it's asking right here. The indefinite integral is just a function. What's going to be in our function? X will be in our function. So what is the indefinite integral of this? Done. An indefinite integral does not have a numeric answer. It has x in it. Does it have to be x? Could I have done that with u instead? Absolutely. Find me the definite integral right here. Find me the definite integral right here. Find me the definite integral. Actually, yeah, that's fine. Just pause in the middle. What does that come out to be? What is that? 2t plus 2/3 t to the 2/3 t to the plus what? T to the -1, and you're evaluating this from 1 to 9. And a great thing to do is just put parentheses around it so you know you're evaluating the whole thing from 1 to 9. So if I asked you, you already just did, what's the indefinite integral of this thing right here? 2t plus 2/3 t to the plus t to the -1, and then to be really complete, what could you put on the end? Yeah, the general indefinite integral, plus c. It can't hurt to put the plus c in there. Because, can it sting you pretty bad not to put the plus c in there sometimes? Yeah. So what's nice about this, does this evaluate pretty nicely? It actually does. Now, it doesn't look, this wasn't so much fun, but I will tell you, it is really common to have to deal with some fractions. It is really common to have to do this. If you have your calculator, on the other hand, is it a little easier? Sure. And if you have your calculator, if this is the calculator portion of the test, what can you just plug into your calculator? You can actually do the integral out. Do you get any benefit from spending 5 minutes doing this integral, even if it's pretty easy, by hand? No. What is your most valuable asset on the AP exam? Time. Evaluating for 1. You're evaluating the functions right here. What are you evaluating? Integral from 1 to 4 of minus 6. And you put a dt at the end here.
What does that mean?
Well, dt is just, you're adding up an infinite number of rectangles. Here's the height, here's the width.
So, okay.
dt means an infinite portion of the t-axis. Infinitely small portion of the t-axis. So dx is infinitely small portion of the x-axis. That's one way to think about it. 3 and -2. So let's just take a look at this. If we were to graph this, is it concave up or down? Up, because the leading coefficient is... So it's going to look something like this, right? Agreed? And we're looking at it from what to what? 1 to 1. So this is actually steeper than this, isn't it? It's x squared is pretty steep. So what 1 to what? 1 to 4 right here. See this, everybody? So based on this picture right here, if that steepness is correct, which it's hard to figure that out, but I think it's a little steeper. Based on that, you're adding up that area. Does it look like it's positive or negative? It looks like it's negative, but are we sure? Because we don't know how accurate my graph is.